All right, guys, glad you could join me. Today, you guys are going to be talking a little bit more about specific heat. Now, here's our objective. Here's ultimately what we're going to do. So, you guys, this is a sheet that you guys are going to be assigned as homework. So, we're going to go over one so you guys know how to do it, and then you guys are going to identify another metal. So, that's the whole objective here today, guys. Here I have a metal, and I want to identify what metal it is. Now there's different ways you could do that. Like you could just determine the density of it, and each substance has its own unique density. But we're going to use what else is unique to a substance is its specific heat value. Remember, that's the amount of heat that would be necessary to raise the temperature of a certain amount of this by a certain amount of degrees. That's the specific heat. You guys, we're gonna just go over the technique. So we're gonna follow this. So it says Pam, or Mr. Willitson, has two pieces of metal. Let's just say I have one metal. She has two pieces of metal, metal A and metal B. We're gonna do metal A today, and then you guys in your homework are gonna do metal B. But you want to, for both, you're gonna end up showing what we're doing here anyways. So those of you guys who are watching the video lesson, I'm kind of giving you guys a head start on your homework. So both are silvery solids, so right, most metals are silvery, so you can't really identify what it is just by looking at it. For each metal, Pam determined its volume and mass. You guys got the volume and mass of the metal, so we're just focusing on metal A right now. Then she heated each metal to 100 degrees Celsius. Okay, so here's what we're gonna do, guys. So how am I gonna heat it to 100 degrees Celsius? I'm not gonna just put it on a hot plate and then measure the temperature once it hits 100 degrees. You guys know that just looks stupid. You're not gonna be able to get an accurate measurement. So the best way to do it is to use what's called a hot bath. So we have some water, we heat it up, and you guys could think 100 degrees should sound familiar to you. There's a significance about that. You guys, the reason why we'd heat it to about 100 degrees is because that's the boiling point of water. Now there's different things that can affect the boiling point, but for the most part, once I bring this water to a boil, I should expect it to be around 100 degrees Celsius, which indeed when they did, they got 100.0. If we were to do this really in the lab, it might be like 99.5 or something like that. So anyways, then she places it in 10 milliliters of water at 21 degrees Celsius. Okay, so what we're gonna do is we're gonna heat this up, and then ultimately, we're gonna transfer it to a calorimeter. You guys remember what a calorimeter is? It's just a device used to minimize heat loss to the surroundings. So basically, I'm gonna put some water in a calorimeter. I'm gonna take my hot metal and transfer it to the water in the calorimeter. Well, you guys think about what's gonna happen. Isn't the hot metal gonna transfer heat to the water in the calorimeter? So the metal's going to cool down and the water's going to heat up. Well, what I'm going to use is a technique to, we're going to use the specific heat formula to figure out how much heat did the water gain, and ultimately use that to ultimately figure out the specific heat of the metal, and then utilize that to identify what the metal is. So we have 10 milliliters of water, so you guys know you'd use a graduated cylinder. So let's say we want to have 10 milliliters of water in our calorimeter. Okay, so you would measure the temperature first. You would make sure, and we measure the temperature of that water beforehand. And the temperature of the water that we're starting with in the calorimeter is 21 degrees Celsius. Okay, so now let's say this is heated up. What I'm going to do is, and you guys know, if you were to do this in the lab, which we normally would, we wouldn't be transferring that thermometer back and forth that quickly, because it's going from hot to cold. You have to let it stabilize first, right? So anyways, let's say it brings it up to 100 degrees Celsius. Let's imagine the water's boiling. Then what I'm going to do is I'm going to take that metal and transfer it carefully to the calorimeter. And then you guys notice I'm going to use a cap here. The whole idea is that we're minimizing heat loss. The whole, theoretically, all the heat that the metal loses is going to be absorbed by the water in the calorimeter. So then the last thing I got to do is measure the temperature of my water metal combination. And so what I should be seeing is the temperature going up, right? Because the temperature of the water was 21 degrees Celsius. I put the hot metal in there, and now the temperature goes up to 27.3. So now I want to show you guys how normally in a lab, right? That's what we do. We collect data, then we analyze the data and utilize the data to reach a conclusion. The conclusion we want to do is identify the metal. So here's how we'll use that. So we're going to use our specific heat formula. Okay, so check this out. First thing we're going to try to do is determine the heat gained by the water. So I'm going to use the specific heat formula. So if I want to get the heat gained by the water, that's Q. So I don't have to rearrange this. It's already solved for Q. I have the specific heat of water. You guys remember, that's what I asked you guys to memorize. The specific heat of water is 1 calorie per gram degree Celsius. Easy to memorize. times the mass of water. Well, how much, now I can see people would look here and they'd say the mass, they want to put 3.99. But you got to remember, this is the mass of the metal. That's what the metal weighed right here, okay? That's not the mass of the water. If I want to get the heat gained by the water, I need the specific heat of water, the mass of the water, and the change in temperature of the water. So, how much water did I put in the calorimeter? You guys notice it was 10 milliliters. But we need a gram mass, right? But you guys remember, once again, this is the nice thing about water. Water has a density of 1 gram per milliliter. That means 1 milliliter of water weighs 1 gram. So if I have 10, and centimeters cubed, that's just another way to say a milliliter. I tend to use milliliter. They're using centimeter cubed. It's the same thing. So if I have 10 centimeters cubed or 10 milliliters of water, it's going to weigh 10 grams. And then how do I get the change in temperature? You guys know, right? It's a before and after. I know some people might be tempted to want to use 100 degrees Celsius. But remember, that's the water here. I'm interested in the water here. Well, you think about it. What is the final temperature of the water? When I looked at I read to the point where it had the highest temperature. That was 27.3. Remember, the change in is always final minus initial. So I take the final temperature minus what the temperature of the water was initially, 21 degrees Celsius. So I go 27.3 minus 21. That's 6.3 degrees Celsius. You guys look at here. Always take into account your units. See if the units work out. Look, degrees Celsius on top, degrees Celsius on the bottom, cancel out. Gram on top, gram on bottom, cancel out. What's the only unit I have left? Calories, which you guys remember is a heat unit, which should be appropriate since I'm solving for heat. So I go 1 times 10 is 10 times 6.3 is 63 calories. That's how much heat the water gained. Now, I want to but you guys remember, ultimately, what are we trying to figure out? The specific heat of this metal. But look at this technique. Look what we can say. Remember, theoretically, we can say heat gained by water should equal heat loss by the metal. Right? So, what do I want to get? The heat. I want information about the metal, right? So I would say, I would use this equation again. Q is equal, but this time, I want to solve for the heat lost by the metal. So, ultimately, we can use this equation, but now, we can use this equation ultimately to identify the metal. And how can we identify the metal if we are able to calculate the specific heat value? You guys see? In this equation, we're using the same equation, whereas there we were getting the heat gained by the water, but here, we're going to solve for the specific heat of the metal. Because then once I have the specific heat of the metal, I can compare it against a table of known specific heat values and determine what my metal is. So, you guys look, now I'm gonna solve for C. I gotta rearrange this. And you guys know how to get C by itself? You just divide by these things, right? And what you do to one side, you do the other. Guys, and that's why they want you to take algebra concurrently with chemistry, because you gotta do some algebra right here, right? So, I gotta get my Q. So the question would be, well, what's my Q? Remember, the Q is the heat lost by the metal. Well, what do we say theoretically? Isn't the heat lost by the metal equal to the heat gained by the water? And how much heat did the water gain? Look, 63 calories. That's why we did this, so we could use that. 63 calories divided by the mass of the metal. This time I'm going to use 3.99. That's the mass of the metal. 3.99 grams. And then times the change in temperature of the metal. Remember, this was the change in temperature for the water. Well, you think about it. What was the temperature of the metal at the beginning? It came from the boiling water, wasn't it 100 degrees Celsius? And then I put it in the water, and then the water and the metal's temperature both went up to 27.3. So what am I going to do? I'm going to subtract these two values. 100 minus 27.3 is what? 72.7 degrees Celsius. 72.7 degrees Celsius. Now, if you look at your units, do any units cancel out? Hopefully you guys will see no units cancel out. So I'm going to punch my numbers, and you know what? Actually, I do have to punch my numbers. So how am I going to punch this in here? I'm going to go 63 divided by 3.99. And then what do I got to do? It's still on the bottom, guys. So you press divide again, divide by 72.7. And I'm going to get 0.217. So my C is equal to 0.217 calories per gram degrees Celsius. Now at this point, I'd say, okay, now I'll attempt to identify the compound. And I know some people will be looking, let's see here. You're comparing against a known, and I could see where some people at this point will go, you know what, 0.217, 0.222, it looks like that's the closest to that. Oh, I think this is 10, but it's not 10. Hoping some people caught on. You guys, this is where you have to look at the units, look at the category units. These specific heat values are in joules per gram degree Celsius. This is in calories per gram. What do we have to do? We have to convert. You guys, in a previous video lesson, I gave you the conversion factor. Let me see if you guys can see everything here. I gave you the conversion factor. 1 calorie is equal to 4.18 joules. If you haven't already written that down in your notes somewhere, that allows you to convert between heat unit in joules to heat unit in calories or vice versa. So 1 calorie is 4.18 joules. So if I want to convert this, 1 calorie is 4.18 joules. Basically, you guys, using unit analysis, I just take 0.217 calories per gram degree Celsius, and then you guys remember we use our parentheses. Calories is on top, so I want to put the 1 calorie on the bottom is equivalent to 4.18 joules. Now you notice that calories cancel, and now what I'll get, joules per gram degree Celsius. Both these unit numbers are on top, so what do I do with them? They're both on top, you multiply them. So I do 0.217 times 4.18, and here's what I get, 0.908. And that's joules per gram degree Celsius. So now that is a specific heat value that I can now use to compare against this table. And based on that, what would you guys conclude our metal is? Bingo! Our metal here is aluminum. It's a rather light metal. If you guys look on the periodic table, it's one of the lightest metals. All right. So, you know what? I'm going to stop there. So you guys on the homework, you guys, I do want to see this work. I want you guys to show this on your on this sheet, and then also you're going to have to identify metal B using the same technique and the data that Pam collected for metal B. All right, guys. We'll see you next time. Bye.